Hi everyone, welcome to lesson 3 of higher chemistry. We are moving on to bonding in compounds today and having a look at the polarity of molecules. So we've already had a wee look at the polarity of bonds. Today we're going to have a look at how that affects the polarity of molecules. So we're going to, just the same as last time, explore some examples of different compounds to learn about the polarity of molecules. So what does this mean? We want to be able to identify a molecule as being overall polar or non-polar based on its symmetry, and I'm going to show you how to do that. So, a recap, polar bonds involve the unequal sharing of electrons. So we're looking at situations where we have a difference in electronegativity which is greater than 0.4, and that will give us our polar bonds. But molecules which contain these polar bonds can be overall either polar or non-polar. So how you figure that out is you have a look at the arrangement of the atoms within the molecule, and that can help us figure out whether the whole molecule is polar or non-polar. First of all, before we delve into all of the polar bonds, remember that non-polar bonds do not have dipoles, so they don't have slightly positive or slightly negative charges. In other words, if you see a molecule which has non-polar bonds in it, the whole molecule is non-polar. Okay, let's have a look at compounds containing polar bonds. We can split these up into two categories, being symmetrical and unsymmetrical. So let's have a look at symmetrical molecules first. We have an example of carbon dioxide here. It has a delta positive on the carbon, which is less electronegative than oxygen, which has a delta negative, a slight negative charge. Now, as you can see here, this is a symmetrical molecule. There are positive and negatives on both sides of the axes, so that means that the whole molecule is symmetrical. Now, where we have a symmetrical molecule, that is said to be a non-polar molecule. So unsymmetrical molecules have a clear positive side and a clear negative side. It's not like we have positives and negatives on both sides. There is a clear positive end of the molecule and negative end of the molecule. And this can be seen in our example of oxygen here, which has the positive up here. So this whole part of the molecule is positively charged, and the negatively charged part of the molecule is down the bottom. And that again arises from the polar bonds. Oxygen is far more electronegative than hydrogen, so oxygen has a delta negative and the hydrogens are delta positive. So when we have this one side and other side, that is a dipole. It's a permanent dipole. It's going to stay there, and that is what we call a polar molecule. So to recap that, if you have a symmetrical molecule where you have positives and negatives on both sides, then you have a non-polar molecule. If your molecule is unsymmetrical and you have a clear positive side and a clear negative side, then that is a polar molecule. Now there is a kind of handy way you can remember this, and that is by remembering the phrase SNP up. So SNP stands for symmetrical is non-polar, and up stands for unsymmetrical is polar. So if you remember that, you can look at a molecule and based on its symmetry figure out whether it's a non-polar or polar molecule. I've put in some more examples. So here are some non-polar molecules. As you can see, there are clear lines of symmetry down both axes. You can't look at a molecule of methane, for example, and say, right, there's definitely a positive side here and a negative side here, because the positives are surrounding the negative. I like to think of it as if you have an imaginary magnet. And if you were able to magnetize and drag along one of these little molecules with your imaginary magnet, then that would be a polar molecule. But as you can see, if you put the negative or the positive end of a magnet near this methane molecule, you couldn't actually attract the negative charge because it's surrounded by positives, if that helps anybody think about it. So where there is symmetry and there is no clear positive and negative side, there is no dipole on the molecule, you don't have a positive and negative side. So these are non-polar examples. Polar examples, so we have ammonia here, which you can see the nitrogen is the negatively charged part of this molecule, and the 3 hydrogens are kind of all clustered at the bottom. That's your positive side of the molecule. This again arises because nitrogen is more electronegative than hydrogen, so it has a delta negative and the hydrogens are delta positive. Because there is a clear negative and a clear positive side, there isn't any symmetry. So that means something called a permanent dipole has been created. Now, we've talked about dipoles forming in bonds before. So if you have a difference in electronegativity, you have a slight positive and a slight negative charge, and that can be referred to as a dipole. What we say when this arises in a molecule is that it's a permanent dipole. This molecule is not going to change the way its bonds are placed. It's going to stay like that. So what that means is the difference in charge, the positive side and the negative side is always there, and that's why we call it a permanent dipole. Water is my go-to example for a polar molecule. If anybody says polar molecule, I just instantly think water, and it helps me kind of visualise that you've got the oxygen, which is the delta negative, and then the other side of the molecule you have your 2 delta positive hydrogens, and that tells me it's unsymmetrical and it's polar. So there is not much to this lesson other than that. What we really have to do is just look at compounds and put this into practice. So we want to be able to identify a molecule, any molecule that you're given, as being polar or non-polar, and having a look at that symmetry, having a look at the bonds. Are the bonds polar in the first place? Do we have to have a look at the symmetry, etc.? So what we're going to do is we are going to make sure that we have achieved our success criteria by looking at some questions. So the questions are on page 6 of your booklet. As always, here is question 5. And here is question 6. What I would like you to do is I'd like you to pause this video right here, go away, attempt both of those questions, and then play the video again and you can hear me go through the solutions to all of these. I'd like you to mark them by yourself, please, and on your assignment upload some evidence that you have completed these questions and also that you've marked them as well. It would be really, really good. A few people actually commented some feedback for themselves the last time I looked at some of these questions. That would be really, really good to see. That means you really, really understand what kind of bits you need to work on for next time and how to actually work on them. So let's start with question 5 then. We are drawing each of the molecules and looking at the electronegativities. Then we're going to draw dipoles if they exist and decide, is the molecule polar or is it non-polar? So let's start with 5A. We have carbon joined to 4 chlorines. Carbon's electronegativity is 2.5 and chlorine's is 3. That means there's a difference which is greater than 0.4, so we're looking at polar bonds here. Now, the molecule has 4 polar bonds. If we put in our dipole, we have a slightly positive on the carbon and slightly negatives on the chlorine. This molecule is symmetrical. It does not have a clear positive and a clear negative side. In fact, the positive is surrounded by all of these negatives. So that means if we think SNP up, if it's symmetrical, it's non-polar. B, we have phosphorus and hydrogen, so 3 hydrogens and 1 phosphorus. Both of these elements have the exact same electronegativity of 2.2. So if there's no difference in electronegativity, we have non-polar bonds, and therefore we have a non-polar molecule. See, we have 3 different atoms in this molecule. We have carbon bonded to 3 chlorines and 1 hydrogen. Now we need to be careful with these. These are a wee bit tricky sometimes if you don't look at them properly. We have 3 polar bonds in this molecule because of the electronegativity difference between the carbon and the chlorine. It's 0.5, which is in our polar range. The carbon to hydrogen bond, however, is an electronegativity difference of 0.3, which means it's in our non-polar range. So this bond here is a non-polar bond. That means that it doesn't have any dipoles. We just leave the hydrogen as it is because it doesn't have enough of an electronegativity difference. So if we leave the hydrogen as it is and just ignore it, we end up with our delta positive on our carbon, just as we did before, and delta negatives on the chlorine because it's more electronegative. Now if we look at this here and just looking at the charges, there is a positive and a negative side to that molecule. You could split it in half sideways, and you could, in theory, pull it along with your imaginary magnet. So if it's unsymmetrical then in terms of charges, then that means it's a polar molecule. And that is your non-polar bond. D, we have hydrogen and chlorine. Chlorine's electronegativity is 3, hydrogen's is 2.2. So we have a dipole here where the chlorine is delta negative and the hydrogen is delta positive. That means we have a polar molecule because there's a clear positive and a clear negative side. E, we have 2 chlorines, so Cl2 molecule. We have no difference in electronegativity here, we have the same element, therefore we have a non-polar bond and a non-polar molecule. F, we have sulfur and 2 iodines. Now the difference in electronegativity here is only 0.1. That does not warrant a polar bond. That means we have 2 non-polar bonds in this molecule, and the molecule is overall therefore non-polar. I don't know why H just came up first, but we'll just do H first. H has N, nitrogen bonded to 3 chlorines. Nitrogen and chlorine have the exact same electronegativity. There is no difference, so these 3 bonds are non-polar bonds, and the molecule itself is non-polar. G, we have a kind of a little exception to the rule here, so I'm interested to see how many people have spotted this. So you have boron and 3 fluorines. Boron has an electronegativity of 2 and fluorine has an electronegativity of 4. Now some of you might be looking at that and think that's not covalent at all, it's ionic because the difference in electronegativity is 2, which is just past the threshold of 1.9 to be polar covalent. But this is just one of these little exceptions to the rule. It's to do with the stability of these ions if they became ions in a lattice. Boron fluoride is covalent in this instance, and because it's got a greater electronegativity difference than 0.4, it's polar covalent bonds. So we draw in our dipoles, delta positive on the boron and delta negative on the fluorine, and we have an overall polar molecule because the top half is positive, a clear positive, and the bottom half is negative. There are a few different reasons why this is covalent and not ionic, but it's way past the threshold of what we have to know. So we're just going to put a wee star at it, say it's a little exception. Well done if you spotted that. but in this instance, it is a polar covalent molecule. Question 6. Which of the molecules from question 1 have polar bonds and are a non-polar molecule? So, if we go back to the very start, we are looking for something that has polar bonds and is a non-polar molecule. The only one here, I think, is A for this, because A is the only one which is symmetrical and has the polar bonds in it. So for 6, polar bonds in a non-polar molecule is A. A bond with the highest ionic character. So if we're looking for something with the highest ionic character, we are looking for a bond with the greatest difference in electronegativity. Remember, think back to the bonding continuum where we have pure or non-polar covalent from 0 to 0.4, and then we have polar covalent from 0.5 to 1.9, and anything over 2 or over is ionic. So that's going to be that example we looked at, which is G, because there is 2 of a difference in electronegativity. Have the least non-polar bonds is 6C, so we're going to be looking for what is the smallest difference in electronegativity here, and that is B, E and H, which all have 0 difference. They are either the same element or they have the exact same electronegativity. So they have the least non-polar bonds. 6D, we are looking for molecules which have polar bonds and are a polar molecule. So that is all of the ones that we named polar, which have a slight positive side or a fully positive side and a fully negative side, where you've created a permanent dipole, and that is the opposite one. So C, D and G are your polar bonds, which are arranged in a way that you have a positive side and a negative side, so you end up with a polar molecule. E, which of the molecules have bonds which are considered to be pure covalent? So pure covalent, as we said before, is something that has a difference of between 0 and 0.4, and in this case we have B, D, F and H. So this is just a little exercise to have you looking at all of these molecules. Can you identify where the polar bonds are, but we have a non-polar molecule, and the highest ionic character is the biggest difference in electronegativity? So we're really just looking to exercise all of the skills that you have picked up in the last couple of lessons and make sure that you know how to answer all of these questions. That is the end of the lesson. You will have a Google form with some past paper questions on it that you can practice answering, and you'll also have an open-ended question you can practice answering. For now, very, very well done if you got those correct. If you didn't get any of them correct, then please, by all means, ask any questions to Mrs. Calder or myself if you need any help. If not, then try and write yourself a wee bit of feedback. What could you do next time? Or is there any way that you can think of something to help yourself? I like doing the SNP up thing because it just helps me remember really, really quickly what symmetrical and unsymmetrical means. If you want to come up with anything for yourself, then absolutely feel free. Thank you very much for your continued hard work. It is very much appreciated, and I hope you have a really good week. Thank you.